All right, so of course the other factor besides the frozen soil is snow. So we're going to talk about the snow modeling capability in GSSHA. So what do we care about snow? So if we're speaking about the United States, at least, if you're in the western United States, the meltwater from the snowpack and then the headwaters provide almost all the water for water supply. And even though the headwater catchments may be quite small, maybe 25% of the total land area, the snow melt from these areas provides, the majority of the water for the annual runoff. And so if you're in a snow dominated watershed, then the snow is everything. And in those areas where there's snow all the time, especially in places like where there's snow at the top of the mountains, but it's dry down at the valley where all the people live, people are obsessed with the annual snowfall. And just in addition to the rough amount of water that comes as snow and is stored in the snowpack, is like the hydrograph timing. So when you got snow, then you have a complete different change in the timing of the stream flow. And so instead of getting this rapid runoff response in a non-snow dominated region, the water is going to be stored in the snowpack until the spring, summer, thaw period. And then the last kind of consideration is flooding. And in like the upper Midwestern United States, when you get snow on rain, that's backwards. When you get rain on snow, you got a big snowpack and you get a big rainfall in that snowpack. That's when you get the biggest, worst, most damaging flooding events. And so those are kind of a critical thing in a lot of different regions, kind of for different reasons. Oh, I had some other cool pictures. So overview of how we do it in GSSHA model. So we look at everything in terms of SWE, the snow water equivalent. That's how we keep track of everything. Now we can spit out approximate snow depth pack and things like that, but we're really tracking SWE. So we have 4 different models inside of GSSHA for snow, and one is an energy balance, one's a temperature index. We have a hybrid energy balance, and we have a radiation-derived temperature index. There is accounting for snowpack dynamics, but we have a single layer snowpack in all the different models. So we also do adjustments to the hydrometeorological forcing data. We call that HMET. And then there's meltwater transport. So once we have some melting in the pack, the water has to flow vertically through the pack. It has to flow laterally through the snowpack. And then, like we talked about before, the frozen ground impedes infiltration to some extent. So let's talk a little bit about the different snow models that we have in GSSHA. The first is just a simple energy balance. So it counts for the energy fluxes between the snowpack, the ground, the atmosphere, and the precipitation. So basically, if you put enough energy into your snowpack, then you get an equivalent amount of melting. Temperature index, this is probably like the most common kind of model you'll find in especially hydrology models. What we have essentially is Snow 17, if you're familiar with that model. So that says the amount of melt within the snowpack is based on the temperature, precipitation, and then a host of calibrated parameters. And because it's purely in empirical, it's got a lot of parameters we have to worry with. One of our colleagues, or previous colleagues, Mike Follum, he came up with this hybrid energy balance method. And that is the default method in GSSHA. In GSSHA, you don't have to tell it to do snow. It's going to be looking for snow, and it's going to model snow. What you pick is the method you want to use. If you don't want to think about it or you don't know, we defaulted to this one, and we defaulted to this one because we thought it was overall, under many different circumstances, the best model. And so what it is a modification of the energy balance model that accounts for snow pack temperature dynamics, the heat deficits. And then there's a radiation-derived temperature index method, which is just like the temperature index method above, but it uses a radiation-derived proxy temperature instead of air temperature in the melt equations. And I'm going to explain that because it's not intuitive to me. I didn't come up with it. Another thing Mike Fallon came up with. Not sure what those arrows are for. So simulating SWE, the energy balance versus the temperature index. And so basically, if you have an energy balance, you're looking at the energy that's coming into the snowpack and leaving the snowpack. And all those Q's over there are energy. And so you're counting for a lot of different things like the net radiation and precipitation heat flux, sensible heat flux, latent heat flux, ground heat flux, and then how those things, you know, the emissivity, the albedo, latent heat diffusion, those all come into play. So this is a physics. This is basically an accumulation of heat, and so it's a physics equation that's solved in every cell. If we're looking at the melt is just, and so yeah, our melt is just we sum up all that energy that goes into there, and we look at the latent heat of fusion, and you know, if you have more energy than it takes to melt the snow, then you'll melt some proportion of the snow. If you're doing the temperature index, you're just looking at, you know, the temperature of the air, and you're driving the what happens inside the snowpack based on the temperature in the air. So it's a much simpler type of formulation. So in the energy balance, in the hybrid, which also is a hybrid energy balance. So those are all the things we look at. So, you know, basically you're looking at how much energy do you have to melt snow, and then you have you account for all the different sources of energy, be they in or out of the snowpack, and that's long wave radiation, long wave emission by the soil, evaporation and sublimation, sensible heat transfer due to turbulence from the wind, and then precipitation. And so we have the simple kind of concept that 1 cc of snow will melt for every 336 joules that you add to the snowpack. And so in this case, we don't account for any snowpack dynamics. We just say it's just a lump thing, and if you add this energy, then you get melt. And that's fairly simplistic. So using the temperature index method, like we said, based on Snow 17 by Anderson, and there's all of his papers if you're curious about how it's derived. So melt occurs once the heat deficit is overcome. So now the snowpack is kind of modeled as a heat deficit, as a kind of a negative heat storage thing, and it has to get this heat deficit. It has to be overcome. So the melt rates are based on the air temperature and calibrated melt factors. Energy balance, if we back up, there's nothing calibrate. That's all just, you get inputs and you calibrate and you run the thing. So there's nothing to do. And temperature index, you've got to relate, you know, the temperature to your snowpack, and you've got to have these calibration parameters: this melt factor, fraction percentage form of rain, wind function, M base, and so you got a variety of factors in there that you have to put values in, and so you have to calibrate this thing. Basically, is the net of it. So the temperature index. So the melt is basically it's a function of the temperature and the precipitation. And so it accounts for two things. It is accounting for the energy and the precipitation, but it's also looking at the air temperature, which is kind of a proxy for all of the factors we had in the other energy balance method. There's another a radiation-derived temperature index, RTI method, they call it. And so it requires temperature, precipitation, and cloud cover. And the nice thing about it is that it looks at other things besides just the temperature. It no longer it doesn't really use the temperature. It uses a proxy temperature. So it's the same equations as the TI method, but instead of using the actual temperature there, you use a radiation-derived temperature, which is the long wave radiation temperature down into your snow, and the shortwave radiation temperature down into the snow. And then based on the thermal capacity of the snow. And so we've kind of gotten away from temperature, and our temperature is really kind of an energy balance type equation. So we kind of we've kept the equations, but now we've converted kind of the basis of it from temperature to radiation. So how do we get the TRAD? So we account for the shortwave radiation and related reductions. And here's just kind of the nice thing about this method I like, is that we look at things like the vegetation shading the ground, or clouds blocking the radiation, and is there topographic shading, like is a mountain blocking the sun, and then how intense is the sun on the land based on the aspect angle. So if the land is very steep and the sun's at a high angle, then you don't really get much sun on the land, even though it like it would if it was flat. So it includes a snow albedo model, and accounts for the long wave radiation from the clouds and the canopy, and that's a radiation that's coming down. So it has a long wave radiation for clear sky, including the emissivity of air, so that you've got to transport basically the long wave radiation down through the air. You increase the long wave radiation due to clouds, so we include that in the model, and then just the long wave radiation due to vegetation. And so Mike and I can't remember who else, wrote a paper about this method if you're interested in it. So methods of simulating the SWE, a quick review of what we just talked about. So there's the energy balance. So it uses energy balance algorithms to determine the melt, but does not include the heat deficit of the snowpack. It treats the snowpack quite simply, and it typically underestimates SWE when the topography is not accounted for in the model. So that's kind of the downside of the energy balance method. The upside of it is there's nothing to do at all. It just automatically will run the thing. The temperature index, so it uses temperature, precipitation, and then a slew of calibrated parameters to simulate the snow melt. And it does incorporate the heat deficit / snowpack dynamics, but it requires calibrate 9 parameters. That's a lot of parameters. And if you're using like if you had snowpack measurements, it would be not that bad. But if you're using, say, stream flow, then you've already got all these parameters for everything else. So if you throw 9 more on top of it, you got kind of a mess. So the hybrid energy balance method, which, like I said, is the default method in GSSHA. So if you don't just do anything whatsoever, you'll just get this automatically. So it incorporates our energy balance melting algorithm, but it includes the heat dynamics, heat deficit snow pack dynamics, and it gets the number of parameters down to a more manageable 4 parameters. And then you can also use the radiation-derived temperature index method, same as the temperature index method, but accounts for kind of how the energy comes in based on the topography, cloud cover, vegetation cover. Again, the downside is, since we basically have our temperature index method, now we've got 8+, and I don't know how that works exactly, but let's just say there's around the same number of parameters to calibrate to. So if you've got a watershed and you've got a gauge for hydrometeorological factors, that's temperature, radiation, dry bulb temperature, wet bulb temperature. It's just a handful of, like, I think there's 7 different things that go into that. So, that's at one elevation, but you're in a snow dominated region. You've probably got elevation differences. You have mountains perhaps. So you have to adjust those parameters based on the elevation. And so there's 3 different ways to do it. One is a simple method, and you define a constant temperature lapse rate, then GSSHA adjusts the temperature. The relative humidity and pressure can also be adjusted. And this is what we mostly use. There's something that Mike called a complex. Let GSSHA automatically adjust the temperature, pressure, and relative humidity based on the mean adiabatic lapse rate. And then punt, if you have the data, you can input raster-based forcing data from an atmospheric model such as GFS or the European model. And then you would have the different temperature, relative humidity, so on and so forth at the different elevations, and you wouldn't have to do any computations let the model do any computations.
Chuck, let me pause you right there real quick.
Go ahead.
A question from Sunil, and I think your last slide helps to start answering this question. He says, does the GSSHA model provide mechanisms such as the use of elevation bands to account for the distribution of precipitation and temperature in complex mountainous regions?
Well, I guess the short answer is yes, but here are your options for doing that.
Yeah. And I put a link in the chat to the GSSHA wiki that describes how you can use these cards and put them in your project, right?
Yeah, I mean, if you have like a thermal inversion or something, then only the third one would provide, reasonable results. The other ones assume that as you get higher, it gets colder, it gets drier. That doesn't work for thermal inversions, which aren't they're not uncommon. So you just kind of keep that in mind. And at one point, we worked with HEC to put these methods into HMS. So as far as I know, that was a long time ago, but unless they've done something new, I think they have the same methods in HMS, or at least some of them. I'm not an HMS user, so I don't know the exact detail. So once you have some melted water, then you've got to transport it. So melt water is transported through the system in several ways. It's got to go vertically through the snowpack. It has to go laterally through the snowpack. We can have infiltration into the soil. We talk a lot about that, frozen versus unfrozen soils. We get overland flow, we get groundwater flow, and we get channel flow. So we kind of have all the stuff we normally have, plus now we have a snowpack. So melt water transport basics. So the flow of the snowpack to simulate is porous media flow. That means we use Darcy's equation to determine both the vertical and the lateral flux through the snow. So vertical flow is typically considered unsaturated flow. And lateral flow through the snowpack is typically considered saturated flow. So the way, basically, if you're flowing down, then you're flowing through the entire snow profile, and that's an unsaturated porous media. If you're flowing from laterally, then what happens is the water goes down through the snowpack. There could be some unsaturated lateral movement through the snowpack. I don't know about that, but by and large, the bulk of the transport is going to be at the bottom of the snowpack where the water is going to pond. You're going to get head. It's going to force the water through the snowpack. So GSSHA uses the SNAP model. That was from Mary Albert. She was at Crail for a long time. And she wrote this model it models the snowpack properties in each computational cell. I mean, the SNAP model is a point model that we calculate the properties in each cell. And that gives us saturation, gives us saturated versus unsaturated hydraulic conductivity. And that gives us effective porosity. This is all of the snowpack. This has nothing to do with the soils, what I was talking about earlier. So meltwater vertical flow. So the meltwater vertical flow is considered unsaturated flow. And so you got a hydraulic conductivity, which varies with the degree of saturation, just like in the soils. We're basically treating the snowpack like the soils. Effective porosity also changes with the degree of saturation. So while flow is simulated through a single snow layer, you can have multiple wetting fronts. So you're kind of like melting in the front moving down, then melting and the front moving down. And that's based on Mary's work, and then Bingstrom. No, I don't know him. I don't know what he did. Oops, some pictures. And so once the meltwater reaches the ground, it's transported as saturated Darcy's flow. Actually, I rewrote this, and we don't just use the land surface slope. We use the head. It's a diffusive wave. I computed diffusive wave using Darcy's equation instead of like Manny's equation. So I rewrote this transport. So that's not exactly right, but the concept is the same. This is basically Darcy's flow with a head-based formulation. Yep. So yeah, it's a lot of stuff there. So GSSHA uses we talked about this stuff, but there's a link if you want to go read that. Handbook of the Great. So the Handbook of Snow, which I guess is great, states that for long-term sustained water yields, the groundwater flow is the most important thing to be considered. And then this is one of our little proving grounds, Trout Creek Basin in California. Just shows you the kind of the timing between. So SWE is like our snowpack, and shows you how it gets built up over the year, and then it melts off and you get the runoff. So it just kind of shows you the relationship between the snowpack and the stream flow. And there's a significant delay in the melting of the snowpack and the stream flow, and a lot of that's due to the fact that the water mostly goes into the ground, flows as saturated groundwater flow. So review of the meltwater transport is its vertical flow through the snowpack, the lateral flow through the snowpack, the frozen ground simulation, and then all of our normal routing mechanisms within GSSHA. So we had a test. Our original test basin was the Senator Beck Basin in Colorado. It has a lot of nice data, is why we picked it. It's small, so it's kind of easier to tease out one process when you have a small basin as opposed to a giant one. So we're really just worried about things like, the snow and the frozen soils. So we have a really good data set up there, basically. And was this going to work? This is a accumulated snow over like a season or multiple seasons. So we have, and then the little yellow line that's turning blue is the stream. And so as we kind of melt off our snow, we get our hydrograph. So where snow is building up, we get some, like, throughout the year, you might get a little periods of where it's, runs off, melts a little bit, runs off, and then finally we get our spring thaw runoff. And then we have our kind of normal hydrology. And then it kind of goes through it all again. So, there were two different SWE gauges at the site, and we looked at our different, let us try all our different methods, the RTI method in the black, the TI method in the heavy dash line, the SnowTherm model, if you're familiar, that is kind of considered the cutting edge snow model, and then our actual measured SWE data in the dots. And you can see that in general, our model does a really good job of both matching the SWE, and we didn't even want to say it in the paper we published, but we actually beat SnowTherm. So at least at these two little sites. So it does a good job of tracking the actual SWE, which is, what you're doing with the snow. Aaron, how are we doing on time? There's a bunch of stuff here I could go over or not.
I think we're on cue for going through the snow demo and the tutorial.
Oh, so cut it off here?
Yes.
Okay. Yeah, this is just going through some more of the kind of validation data. So we can kill it here. I'll give up control. Or can you just take back? I'll stop sharing.
There we go. I'll let Chris walk us through, but I wanted to show y'all where things are at really quick. There we are. So the GSSHA wiki, if you go to the front page, you scroll down a little bit, we've got links here for the class. The presentations, I've zipped them all up already so y'all can see them there. We have the WMS Learning Center, which is where you can find the snow melt model the tutorial that Chris is going to go through in just a moment. We have a spreadsheet there, so as you go through the snow melt model and as you sort of plug in those different options that Chuck talked about, you can get your outlets, hydrograph and plug it in there and see the differences. And then later on, the permafrost tutorial that Nawa will walk us through and Chris as well, is there. So to start with, if you want to download and follow along, the WMS Learning Center gets you to here. It usually pops up like this. Then click on the WMS Distributed Hydrology. Scroll down to Snowmelt Modeling in GSSHA. The PDF is the instructions for how to do it. This zip file is the actual data that you can start from. Load that up in a WMS and then walk through the tutorial steps that are in the PDF. So hopefully y'all can all follow the links right there. All right.
Sure. Share my screen again.
Rosie had a couple of comments while Chris is pulling that up. She said HMS 4.12 has temperature index and energy balance methods, as well as she said, looks like better results for subalpine rather than alpine from the Senator Beck Basin. Good comments. Thanks.